Hi there. So in previous video we looked at how to delete a node from single linked list. But now here we will look at how to delete an entire single linked list. Let's imagine that this is our single linked list over here and we want to delete entire single linked list. The process is very simple. All we have to do is we have to disconnect head and tail references from the first and last nodes from this single linked list. If we manage to delete these references, this means that we are able to delete the entire list. The reason for this, if first node is not referenced by head, then it will automatically becomes eligible for garbage collection. So the garbage collector deletes the first node. Then it continues to the next node. One more time here, if this node is not referenced any given node, the garbage collector will delete this node over here. So it will continue until the last node. Here it will not delete the last node because last node is referenced by tail. So we need to break this connection over here also. So let's set our head value to null and see what's happening. So if we set this value to null, we see that the connection between head and first node is broken. So the garbage collector will destroy this node over here. So after destroying this, we see that we don't have any connection to the second node over here, so this eligible for garbage collection, so it will destroy this node over here as well. Then it continues to the next node, and next node will be destroyed by garbage collector as well. But when it reaches the last node, it's not deleting this one because here the last node is referenced by tail. So we need to set tail reference to null. This breaks the connection between tail and last node, which means that the garbage collector will delete this node over here as well. So the last node is get deleted. So as you see, by setting head to null and tail to null, we are deleting entire single linked list. Now let's see how this is working in practice. Let's switch to Visual Studio Code and write our delete entire single linked list method over there. So here inside single linked list class that we created before, we will create new method which is called delete entire single linked list. So I'll declare method like this: delete entire single linked list, and this will take as a parameter self. Then here one more time we need to check if the list exists or not. So self dot head is none. Then we print out saying that the single linked list does not exist. Then in else condition we will set head value to none and tail value to none. With this we are deleting the reference between first node and head and the last node and tail. So this is our function. So let's see how this is working in the real life example. So one more time, I haven't deleted the code that we created before, in which we are creating single linked list and inserting elements to it. So here I will run this method for this single linked list over here. But before running, I'm just printing out the values of single linked list. Then after running, I'm doing the same operation over here. So let's save it and run our code. You see that this was the initial version of our single linked list, and after running this method, our single linked list does not exist. So we deleted the entire single linked list. So you might be interested, what is the time and space complexity for this operation over here? The time complexity for this method over here is O1. Because here in the first condition, we are just checking the head value and printing out some text. This is O1 time complexity, and in the else condition, we are just setting head and tail to none. And this is also O1 time complexity, which means that deleting an entire single linked list is O1 time complexity. And you might be interested, what is the space complexity? The space complexity is O1 because here we don't need any space to perform this operation. So the space complexity is O1. So that's all for this video. In this lecture, we have learned how to delete entire single linked list and what is the time and space complexity for this operation over here. Now in the next lecture, let's look at what is the time and space complexity for all operations of single linked list. See you over there. Hi there. In this video, we will recap the time and space complexity of all operations that we have learned till now on a single linked list. The first operation is creation of single linked list. Here, the time and space complexity is constant operation. The reason for this, we have to create a head and tail and first node which take constant time. And similarly, the space complexity for this. And similarly, for space complexity, we have to create only one node and two reference variables. So this is also a constant space complexity operation. Now the next operation over here is insertion. And we have learned that the time complexity for this operation in the worst case is On. The reason for this is that if we want to insert a new node in the middle of single linked list, we have to traverse starting from the beginning till we reach the location that we want to insert the new node. So in the worst case, this might take On time complexity. But the space complexity for insertion is O1 because we just need to create one node. So the next operation over here is searching. This is a searching for a value in a given list. Here again we need to traverse to find a given node. We might traverse till the end of the single linked list nodes, which takes On time complexity. Here again the space complexity is O1 because we only use a variable inside loop which takes constant time operation. The next operation over here is traversing, and it's obvious that it takes On time complexity because we have to loop through all elements of single linked list, which is On time complexity. Space complexity again here is O1 because we use temp variables only inside loop. Then the next operation is deleting a node from a single linked list. The time complexity for this is On because we need to traverse through the list to find a node for deletion. In the worst case, we might traverse all elements, so this will take On time complexity. And space complexity over here once again is O1 time complexity because we use temporary variable only inside loop over here. So finally, deletion of linked list takes constant time operation because we just need to delete references from head and tail, and the rest elements will be deleted automatically by garbage collector. The space complexity over here is O1 because we might use only temporary variables. So with this we are concluding our single linked list. So that's all for this video, and in the next lecture we will learn another type of linked list, which is circular single linked list. So with this lecture we have completed first type of linked list, which is single linked list, and thanks for your time and see you in the next video. So now we have finished learning all types of linked list and explored different operations that can be performed on linked list. Now in this video, let's compare the time complexity of all operations that we perform between array and linked list. It's very important to do so because knowing the time complexity of different operations on these data structures helps us to select the best option for our case. By the end of this video, you will be aware of in which situation array is better than the linked list, and similarly in which situation linked list is better than an array. So let's start to look at these operations one by one. So the first operation here is creation. So we know that creation of an array takes O1 time complexity, and similarly creation of linked list takes O1 time complexity because here we are just creating a node and assigning a value to it. So the next operation is insertion, and we know that we can insert an element in three different ways. So insert an element at the beginning, inserting an element at the end of collection, and insert an element in the nth position. So let's look at these three cases one by one. So inserting an element at the first position is constant time operation for both array and linked list. And similarly, insertion an element at the last position is constant time operation for both data structures over here. So as you see, insertion an element at the last position for array and for linked list is O1 time complexity. Now insertion of an element at the end position is better in arrays than linked list in terms of time complexity. This is because if we want to insert an element at the end location in an array, we can directly go to that location based on the index and insert value there. On the other hand, in case of linked list, it's On time complexity because if we want to insert an element at end position in linked list, we have to traverse through linked list until this position over here. So we know that traversing through linked list takes On time complexity. That's why inserting an element at end position takes On time complexity. Now the next operation is searching operation. So here we will look at first searching an element in an unsorted data. Here it takes order of n in array, because to find an element we need to traverse from beginning of an array to the end until we find the element that we are looking for. In case of linked list, it's also same, because here again we need to traverse through linked list to find the element that we are looking for. But if we are searching for an element in sorted data, in case of an array it is O log n. Because here we can use binary search algorithm, so the logic behind the binary search algorithm will be explained in the upcoming lectures. So here I'm not going to in details, but here I just want to mention that it's applicable for sorted data, and if we used in array, the time complexity for searching will be O log n. So in case of linked list, if we are searching for a value in a sorted data, it's again O n time complexity, because here again we need to loop through the data until we find the value that we are looking for. So it takes O n time complexity. So the next operation is traversing. So it's obvious that for both data structures it's O n time complexity, because here we need to visit each and every element of collection and print its value. So here for both of them it takes O n time complexity. Now the next operation is deletion. So here again we have three cases: deleting the first element, deleting the last element, and deleting the nth element. So deleting the first element in case of both array and linked list is constant time operation, because in case of array we are just deleting the element based on the index, and in case of linked list we are just changing the references of the node. So now the next operation is deleting the last element. So deleting the last element in case of array, it's constant time operation, because here we can directly go to the last cell and delete the value based on its index. But in case of linked list, it depends on the type of linked list. So deletion might take O n time complexity or constant time operation. In case of single linked list, it's O n time complexity, but in case of double linked list, it's constant time operation. So we have explained these cases in our previous lecture. So if something is not clear, you can go back and watch these lectures related to deletion. Now the next operation is deletion of n element. Again here, in case of array, it's constant time operation, because here we can just directly access an element and delete it based on their index. But in case of linked list, it's O n, because here we need to traverse through linked list until we reach the nth element and delete the element from there. So it takes O n time complexity. Now the next operation is deleting an entire data structure. Here, in case of an array, it takes O1 time complexity, but in case of linked list, it depends on the type of linked list. So if the type of linked list is single linked list, it's constant time operation, because here we are just updating the tail and head references. But if it is double linked list, we need to traverse through double linked list and update the all nodes previous values. So this takes O n time complexity, because here we are visiting each nodes of double linked list and updating the previous values. So this is why it takes O n time complexity. Now the next operation is accessing nth element. So we know that accessing an element in the array is done based on the index, so we are just writing the index name and accessing it. So the location of cell in the memory is predefined. That's why accessing an element in array based on the index takes O1 time complexity. But in case of linked list, to access an nth element, we need to traverse through linked list until we reach this element. So that's why it takes O n time complexity in the worst case. So this is all for this lecture. And with this lecture, we have completed another section which is called linked list. So in this section, we have learned 4 different types of linked list and performed various operations on them. We have also learned what is the time and space complexity for these operations that we performed on different types of linked list. Now in the next section, let's see interview questions that are asked by big companies like Apple, Amazon, Facebook, and Microsoft during their interviews that are related to linked list. So see you in the next section.